All right. Hello, everyone. Thanks for having me. So today I'm going to be covering a topic that might be foreign to LabVIEW programmers. We are going to be looking at pointers in LabVIEW. I'm going to show you a little library that I got introduced to back at Blue from a colleague, the LabVIEW Memory Manager. So before we dive in, I just want to do a quick intro. So I am Sam Kaley. I'm a senior staff software engineer at JKI. Basically, that just means I write LabVIEW code, and then sometimes I manage projects as well to see things across the finish line. I've been with JKI for about 7 years now, with a 1-year gap year at Blue Origin. Prior to that, I was at NI headquarters in Austin as an applications engineer. And then prior to that, was at University of Washington, where I got indoctrinated into LabVIEW at an internship at S5 Solutions. So kind of coming full circle, starting in Mukilteo and ending up back here. I am a former LabVIEW architect and CLED embedded developer. Hoping to score some points here today to get those renewed. So shout out, shout out NI for the program to allow us to get those LAPS certifications. But being an EE major, I really gravitate more towards the real-time FPGA side of things. So I was eager to get my CLED, but then once I got it, it kind of felt like I proved my that I knew how to work my way around the CRIO. And lastly, I wanted to just give a quick little plug to the product that I primarily work on at JKI, which is StarGoat. And that is a lovely little acronym that stands for the Strategic Tester for Aerospace Research, Ground Operations and Acceptance Testing. Also the GOAT of stars. Basically, this is a data acquisition and control software we use primarily for aerospace and rocket engine test stands, but it's really just kind of general purpose that runs on RTPXIs, CRIOs, and the like. I bring it up, one, because I'm proud of it. It's something I work on all the time, and definitely check out that website to get a little taste. And also because later on in the presentation, I'm going to use some examples of where I use the LabVIEW Memory Manager inside of this application. All right, so to get started, let's just talk about, has anyone used the LabVIEW Memory Manager? Is this, okay, we've got one from my ex-colleague. Oh, and Michael, okay, so does anyone who hasn't used it have any idea what this is? Yeses, yeah, shout them out. Let's go, yeah. What? Do you have an idea of what the LabVIEW Memory Manager is? Oh, no idea. Okay, we've got no idea except for the two that have seen it before. All right. Well, as the title of this presentation alludes to, it is for allocating, deallocating, and manipulating memory in LabVIEW. So it allows you to create pointers, and I'm going to go with a baseline. We're all generally familiar with pointers. Anyone not familiar with a pointer in coding? Okay, cool. So it allows you to create pointers and allocate memory and then access that memory and share that memory with, well, across your LabVIEW application, like by reference, and also to other applications, which we'll explore. So the three main functions of this library are allocate, move block, which we'll talk about extensively, and dispose. So these two here, let me find my mouse here. We're just going to create a pointer of a certain size. The move block is the kind of interesting one we'll explore in the following slides that allows you to read and write this memory space and then dispose. So your standard open, read, write, close API. And interesting thing is, this is just a call library function node where our library is simply the LabVIEW DLL. So this is native to LabVIEW, and we'll explore kind of how to use this call library function node as we move on. So why might you use this? So one is low-level memory operation. So you declare memory space, and you're given a pointer to that memory space, and you are directly accessing it. So this is a good question. I believe it's just on a general palette. So if you drop a call library function node and just type in LabVIEW as your library, then it's going to access the available functions in the LabVIEW DLL. Yes, yeah, you can see them, in this drop down here, this function name drop down. Any other questions? Cool. There is some NI documentation. It's limited, so you can read about it here. There is some though, but yeah, I believe if you Google LabVIEW Memory Manager, and what we're going to see here in a couple slides is actually a wrapper developed by the NI Systems team that makes it a little bit easier to use. Okay, so it allows you to access low-level memory directly. So it's nice and fast and a little dangerous. And it allows you to interface with external code modules. So this is part of some of the examples I'll show is you can actually get a pointer from a DLL and access the memory space of that DLL and vice versa. You can create a memory space and then pass a pointer to the DLL. So it kind of unlocks these doors in terms of sharing memory across application spaces. All right, so let's take a look at a real simple example. So here we are allocating a pointer of a certain size. That size here is just the size of our array that we're initializing here. So 5 doubles times 8 bytes per double. So we're getting a memory space of 40 bytes. And that's just going to reserve that memory space and give us a pointer to the start of that memory space. Yeah. Yep, exactly. And I've got a couple examples that I'll show you on that. But so right now we're just in LabVIEW. Right now we're just creating an arbitrary memory space, a contiguous block of memory. Yeah, go ahead. Oh, yeah. You gotta get. So his question was, you can use this to share. Actually, could you repeat it?
To call functions from arbitrary DLLs which have pointers as parameters.
Yes, so you can use this memory to call functions from arbitrary DLLs that have functions that have pointers as parameters. Sorry, and if you didn't catch that, I have an example that does exactly that. Okay, so here we are. So we've allocated our pointer. Whoa, this is very sensitive. Sorry, I can not. I'm trying not to use my mouse. Here we are. We've allocated our pointer, and the first thing we're going to do is call move block to write to that memory space. So here we've got our pointer address. We feed that into the move block destination terminal, and the source is going to be just a value of 5, and size is 8 bytes of a double. And then for our read, our source is now flipped. It's the address, so we're reading the address, and the destination is where we're putting that data. And so we pre-allocate this array, and then the move block will take the data and put it into that updated array location. So, and then we have our dispose pointer. So I'm going to kind of dive into this a little bit more because it's a bit odd using the move block for both the read and the write, and you can kind of see how the source and destination flip. So let's take a closer look at that. So for writing, the source terminal is the value that we're writing, whereas the destination is the address that we're writing. So you can see here in this first example, as we saw on the last slide, we're just going to write a single value, and the destination is the address that we're writing to, and again, size 8 bytes. This VI is polymorphic though, and we can actually feed in an array of data. So now our source is an array of 1 and 2. And what I'm doing on the destination is I'm actually taking that address, the pointer that we had before, and I'm adding 8 bytes to it. So now I've actually shifted over my pointer size of a double, and now I'm writing to the memory space of elements 1 and 2 is 0 index of the array. And now my size here, I'm saying, okay, I'm actually writing 16 bytes instead of the 8. So to configure this guy with the call library function node, what you're going to do is you're going to set the source terminal to be adapt to type. So that gives it that polymorphism, so we can wire in anything we want into here. It doesn't actually have to be a double or double array. However, whatever you want to write to that memory space, as long as you read it in the same way back, you can do so. And then the destination here is just I guess I skipped over this part. So we have adaptive type, and then the data format is array data pointer. So basically, this just means we're actually passing a pointer to this data object to the move block function. For the destination terminal, this is just a numeric that's by value. And the key here is the data type is a pointer-sized integer. So this allows the library to be cross-platform. So it'll work the same whether it's on 32-bit, 64-bit. This integer pointer will be the appropriate size based on your target. So this allows you to build apps that you can run on Windows or on RT Linux. Right. So now let's take a look at the read. So again, as I mentioned, the source terminal ends up getting flipped here. So now the source is where I'm reading from, which is that address, and the destination is that pre-allocated buffer here. And so you can see when I run this code in combination with the previous slide, we get 5 as the first data point, and then 1 and 2 as our second. So you hear 5 is the first, 1 and 2 as our second and third data. So his question was, is move more of a copy? And I think it's semantics, because you have to understand that the memory that we allocated has to be moved from the back end into this updated array data cluster, into like the LabVIEW memory space. And those are two separate things. This right here, this updated array is not the same memory space as this address, right? That's why we give it this buffer, so it can move the data from that address into our LabVIEW. Yeah.
File analogy. It's confusing. You see, moving means remove.
Oh, yeah.
Copying is creating a copy of the data in the destination.
Yeah. So for those that didn't catch his analogy, saying moving it would imply we're removing it from the memory space, from the source, but really we're taking that data and copying it from the source and pulling it into LabVIEW. So yeah, that's an interesting distinction. Yeah, thank you for that. Alrighty, so configuring this guy. So it's flipped of what we saw the last time. So now your source is your pointer-sized integer, and you're passing in the value, and your destination is that polymorphic adaptive type, and your data format is the pointer to said polymorphic data. So if you followed me this far, appreciate it, but I can understand this is a little kind of tricky to remember. I don't want to have to, go into my call library function node and remember to set the data types and all of that. While handy, it does, it does have some value to give you that flexibility. However, if you don't want to mess with that, in comes the LabVIEW Memory Manager toolkit. So this is a wrapper around those call library function nodes that abstracts all of the nonsense for you. So this is what was introduced to me by my ex-colleague at Blue, Ryan Paulos. So shout out Ryan. He wrote this with colleagues on the NI Systems engineering team and was gracious enough to open source it and post it on GitHub. So feel free to go download this and play around with it. At the end of the day, it's just a wrapper for those VIs I just saw you, but it has a ton of benefits. One, it does error checking in terms of your addressing, so it makes sure you're not accessing memory that you shouldn't be, and it's highly optimized for performance, so you can kind of dig in there and see that it is meant to go fast, and that's one of the reasons I'm a big fan of it. But here, we have the exact same example. We are doing an allocate, then we're writing to the first element, the 55, and then here we're doing another write, but we're adding, this is the offset input. So again, I'm shifting over 8 bytes, writing a 11 and a 22, and then again I do my read, and I have to give it that pre-allocated buffer. And we'll actually see, I actually discovered this today. We'll see that there are no extra buffer allocations when you do this. The buffer allocation only happens when you pre-initialize. So that, in terms of performance, is really beneficial in terms of avoiding dynamic memory allocations, which can be really expensive for high performance operations. So this library comes with the writes and reads are polymorphic. Wow, I keep hitting the scroll on my mouse. Anyways, So writes and reads support all your standard data types. So all sorts of ints, doubles, singles, etc., as well as strings. Be careful with those. Very easy to get off by one or many. And then it's also got a nice little API. I'm not going to get too deep into this. This is a bit more advanced. We will explore a couple of these VIs in some of the following examples. And so with that, okay, so I'm going to pause there. Next up, I'm going to kind of dive into some example applications of this. But any other questions, front man?
So this is faster than resizing the array. With the dimensions.
So resizing, I would say not necessarily, right? Here you have to know how big it is, and you're not really going to resize it. You can't request memory and then request more memory right next to that. But in terms of like a replace array subset, I would imagine so, or at least.
In the array in your example.
So question, no, I'm not increasing the number of elements. Here. Correct, yeah. So here, the allocate is allocating 40 bytes of memory, which is just the size of my array. Meep. So this is just building off of this guy here. So here I'm allocating.
So you don't change the size of the array at all?
Correct, yeah. I allocate a size 40 bytes, and then I'm just writing to that pre-allocated memory space. I'm not changing the size of the memory.
Okay, and the question is this faster than if I pre-allocate with a standard convention array function?
If you pre-allocate and then do like a replace array subset?
Which is always advised. Do not resize the array
yeah. So yeah. So the question is this operation faster than a replace array subset? If you basically pre-allocate the array and then replace all of this, and I'm going to go ahead and say I don't know. I did not benchmark that. I did benchmark the read and write speed of a pointer versus a DVR, which we'll see in a few slides, but I did not actually benchmark the replace array subset. My guess is in this particular example, it's such a small size array that you're not going to see a substantial difference. So it totally depends on kind of the application. No, size does not matter. Right, yeah, especially if you're doing it in a loop or something, right? Yeah, absolutely. Maybe after this I can whip together a benchmark and show and see. But I don't have the answer, so I don't want to answer. Oh, yeah, Michael. So the question was, does this support fixed type data points? And my guess is yes, because this move block doesn't actually care what you're writing to. It's again that adapt to type. So you can wire anything in there, and then it's just going to take those bits and put them into LabVIEW. The trick is when you read it back, you have to read it back with the same data structure, and then it will take those bits and put those into the data structure. You'll get yourself into trouble if you try to interpret bits that on a data structure that it's not intended for. Correct. It's just raw bits. Yeah, bytes. Yeah, yep, exactly. Yeah, exactly. So this library is, I think, really cool, but it's also pretty dangerous. Like you can mess up very easily, and it's not, type safe or anything. I learned about it like 4 or 5 years ago. Yes, in the back. 5 years old. 5 years old, and I learned about it 4 years ago. Yeah. Any other questions? Cool. Oh, you're on time. Yeah, actually, right on schedule. All righty. So I'm going to show you a couple applications. I'm going to keep it real simple, so you'll have to use your imagination, or maybe we can have a discussion of like how you might use this in more complicated. But just to kind of get the point across, we're going to start with adding two numbers. So all right, so this is a simple add. It is taking an integer x and an integer y and returning the result as an integer. This is all by value. I'm just starting on a baseline. This has nothing to do with the memory manager yet. So how do you do this in LabVIEW? Or how do you call this? This is built into a DLL. This is your interface. How do I call this in LabVIEW? Well, most of you probably would guess and would be correct. You use a call library function node, point to that DLL, and then specify your arguments here. So we've just got arguments 1 and 2 that are just integers, and we pass by value. Lo and behold, 1 plus 1. Oh, I've got a plant. What if they're pointers? Thank you. I knew I could count on you. All right. This is C, yes. And this, I just kind of whipped this example up for this presentation. But yeah, so okay, so now what if our inputs are pointers instead? Now it's not as simple, but still doable with just the pure call library function node, because you can pass a pointer to value. So again, I'm just gonna go back real quick. Here the X and Y arguments, we're passing the value. And this in itself, I didn't know about until I started exploring the LabVIEW memory manager. But yeah, with call library function nodes, you can actually pass a pointer as an input. And so here again, we get 1 plus 1, or excuse me, 1 plus 2 equals 3, without having to use the LabVIEW memory manager.
That's what C programmers like to use. So
yeah, it's everywhere.
Value and interacting with a DLL, which have functions with pointer parameters.
Yes, thank you. To repeat, this is the biggest benefit of interacting with DLLs that have pointer parameters in their functions. Agreed. However, the call library node function falls short. What if the function returns a pointer? So here, again, we're taking in integer X and Y pointers, and we're adding them together, and we get some variable, and then we're returning a pointer, that's that little ampersand, to the sum. And so that sum is a memory space that's stored in the DLL. And if you were to call the function the same way you would do in the last slide, what you're going to get is 1 plus 2 equals 1.5 e to the 7 or 8, or that's probably not right. I'm not great at math, but that seems off. Yeah, exactly. So this is clearly an address, right? Or the context clues should tell us that that is wrong. Now, this would be solved if we could just go into the call library function node and say, this is a pointer, right? Why this dropdown does not have the ability to say pass pointer to value. It just is what it is. So in comes the LabVIEW memory manager. If I want to access that DLL memory space, what I can do is I can call my add. It's going to return me that address, and then I call this encapsulate function. So this is different than the example we saw previously where we were calling the allocate function. Encapsulate actually does not create a new memory space. It takes your address that you provided and then just creates this pointer object that says, okay, as if I allocated it, this memory space is where I'm going to operate. And so you specify the size. In this case, it's just an I32, so it's 4 bytes. And then I can operate it as if it were a pointer that I had allocated. So then I call my read, and again, I have to give it that pre-allocated buffer. In this case, it's just a single element, and I get 1 plus 3 equals 4.
What's the type?
What is the type out of encapsulate? Like this blue wire here, that is the class. So if I go, it's this. It's this class here, my pointer class. All right. Okay, so then let's take it one step further. This part's unnecessary, but just to kind of show how it works. If I wanted to actually pass pointers into my X and Y variables, I can do so by calling the allocate function for both my X and Y. I write my X and Y to that allocate, and then I can call the get address function. And then I pass get address into my add pointers function. And over here, instead of passing it by pointer to value, I'm just passing the value. And again, here we see the pointer size integer kind of trick here. So in this case, I'm actually passing the address to my DLL, and then my DLL is dereferencing that and then adding it. And again, here we see 1 + 3 = 4.
Is there a table somewhere in that communication which explains which data type we should choose for which type of pointer? Terms and that.
Yeah, great question. So he asked, is there documentation that tells you basically how to configure the call library function node to equate it from LabVIEW, point, and C, and kind of establish that relationship? And short answer is I don't know. The way I do it is I go dig into the LabVIEW Memory Manager toolkit and see how they did it, and then I copy that. Yes, yeah. So Michael says probably not.
So you can try all of them, we see what works.
Yeah, exactly. And you only crash LabVIEW n-1 times. Yeah, well, and that's kind of one of the reasons I wanted to show this library here today, is because it's kind of a hidden gem. It's not something that people are super familiar with. It's not well published, but it has its niche. And it's not the end all be all. The title of my presentation kind of implied it was like the greatest thing ever, but they asked me for a title and I kind of panicked. I was like, oh, it's got to sound catchy. But anyways, let's continue here. So next example, we're going to look at the polymorphism of the move block function. So again, keeping it real simple here. In C, I've got a struct called myStruct2, real creative, I know. It is an I16 and a U32, just right next to each other. And then I've got this function, getStructPointer. And the 2s on all of these is because I was messing around and had several iterations, and this is what I landed on. So what the struct pointer is going to do is all it's going to do is it's going to initialize my struct that I've called cluster data 2, just give it some values in there, and then it's going to return a pointer to said cluster. And so in this case, I call my function, and it gives me my address. And we could use the allocate function, or excuse me, the encapsulate function. But the LabVIEW Memory Manager doesn't support my unique data type here. That's not that crazy, but it doesn't have this out of the box. You can, kind of sidebar, you can actually override the pointer class and create your own override that supports your own custom data types, which I've done in instances where the DLL had several kind of unique structs. But anyways, back to this. So here, in LabVIEW, I've got my cluster of 2 elements, and that happens to match my struct, and I specify my size, and I run this, and I give the source as my address, and I'm able to dereference that, and I see 11 and 22 here. Now, there's something fishy here, which is the size of this read is 8 bytes. However, my struct is I16 and I32. Quick math, this is actually 6 bytes worth of data. 2 on the 16 and 4 on the 32. Again, I got my basic math down here. This is a kind of a quirk of C more than anything, and I believe it's called bit packing. But basically, C sees this struct, and it actually thinks it's more performant, more optimized to add padding in between the I16 and the U32, so that this struct ends up being 8 bytes, because that's a more easily useful size of data structure to move around in C. So I have to work around that, because if I were basically what we're going to see here is my struct here is actually an I32 and a U32. So it does not match this data structure. And that's because I'm actually just kind of implicitly adding that padding of the 8 bytes that I'm just, or excuse me, the 2 bytes that I'm just ignoring, the 8 bits. And it allows me to read. If I didn't have an example of this, but if I instead had this as an I16 and ran this, you would see the interpretation of the data would be way off. You'd get the 11, but this Y value would be, it would be reading the wrong subset of the memory space. So just something to be aware of. Also very possible to crash LabVIEW when you don't know about this. So some tricks I've learned here are using the C function's offset of, so I can supply my struct and the parameters within my struct to tell me where that data is within the struct. And then you can use size of to give you the full length of it. So you can kind of use this to inspect your data and then better interpret it. So when I was putting together this example, I actually started with a slightly more complex data structure. All that's different here is it's got an array inside of the struct as well. And when I ran this, it did not work. It crashed LabVIEW a lot. And for the life of me, I couldn't figure out why. And to this day, I still don't know. Maybe I will give someone bonus points if which are really valuable, if they can figure out how to do this, because I'm not convinced it's impossible. But the conclusion I came to was that LabVIEW was representing the struct slightly differently than the way C was. And so LabVIEW could not interpret the bits perfectly, and so it dies. And I even, like, I went all U32s to try to dodge the bit packing stuff. It didn't work. So what did I do? Well, I have access to the address. So I can, I can go in there, so I get my address here, and then I can just read each thing individually. So here I can start at my address, and I can read the first X byte, or X value, and then I take my address and I just add 4 bytes. So I just kind of scoot along my little memory space, and then I read the Y. And then I add another 4 bytes onto that, and then I read my array, and voila, I have my output cluster. So you can kind of imagine that you could wrap this in a pointer class override, a child override, to be able to interpret data structures that you might otherwise not be able to with the native polymorphism. But again, I feel like you should be able to do this. I just cut my losses at a certain point. I was like, I need to move on to the next slide. So, all right. So just quick summary. So of kind of uses of the LabVIEW Memory Manager. So as we've seen, you can share pointers to and from the application. You can either get the pointer from the DLL and access the DLL's memory space, or you can create a memory space in LabVIEW and give that to the DLL. And you can also access kind of pieces of that memory block rather than having to get the whole darn thing. And ... there might be other ways too. Who knows? Things to be aware about. It's very easy to crash. I crashed LabVIEW probably like 50 times trying to put this presentation together, but it crashes pretty quickly. And if you're so it's a quick iteration cycle. And then be careful about invalid polymorphic memory interpretation. So this is kind of what I was talking about on that last slide, is you might think the bits are stored in one way and they're actually stored in a different way. So it gives you an opportunity to kind of see what's going on under the hood, whether you want to or not. And then the other thing I want to call out is, as far as I know, there's no mutexing. So for those that aren't familiar with mutexing, it's basically locking the memory space so that you don't get into a situation where you're doing a read and halfway through your read, someone starts writing to it. And so you get like this race condition where you're half updated, half not. So DVRs, for those that are familiar, which we'll actually explore here in the coming slides, have mutexes built in, right? You've got that in-place element structure, and when you're inside of that in-place element structure, no one's allowed to write to it. As far as I know, these APIs are not mutex safe, so be careful of that. I've never ran into an issue with it, but as just in terms of like good programming practice, probably good to have a handshake or something like that. But if you're trying to go fast, just go crazy. It's fine. But I take no responsibility. All right, and there's probably other things you should worry about too. In the interest of time, I'm going to keep moving. But I guess, well, I'll pause. Is there any questions, or anyone want to pose any other usages or things to be Clear of? Yeah. I'm not sure I fully understand. So you were asking if this is a use case to lock the code for like locking a memory space and give it. Mm.
It will work only on Windows.
Yeah, so like you would distribute a DLL to protect your source code so people can't get in there and start messing with things. Yeah, absolutely.
You cannot recompile it and make it work.
Yeah, actually, yeah, I'm not gonna get into it.
Does it all the time. You dig into those even faster than the bottom you hit is some function, DLL function fault.
Oh yeah, it's DLLs all the way down, right?
And then boom, what are you gonna do with that?
Yeah, and that, yeah.
Is it possible the first element of the array size in LabVIEW? Is it possible the first element is the array size in LabVIEW but not this?
Ah, that's a great. Yeah. Yeah. All right, shout out Brian. You get bonus points. What's that? Yeah, yeah. Good work. No, that's actually a really good guess. I like that a lot. All right, anything else before I move on? All right. Okay, so a couple more examples just real quick. So this is actually an example of when I chose not to use the LabVIEW memory manager, but I was stoked to try it and I'm still stoked to show it off. So this is actually a Stargoat use case. So we added a module to communicate with Profinet, but we didn't want to write any Profinet because that's hard. And there's cards that do it. So we had this HMS card that spoke Profinet and connected to our customers' devices and got all of the data, and it put all of that data into this, what they called it, wow, this is so sensitive. What they call a ADI, which is like a data interface. Basically, data space. This FADI extas read was my data, and I wanted it. So I created this function that gives me the pointer, and I return that pointer. And then I encapsulate the pointer, store it in my class, and then I have this lovely API that reads the pointer. And you can see over here, this is me reading that pointer out. And that worked, first try. Probably didn't even crash LabVIEW. I might have, I don't remember. But then we started thinking about mutexes, and we got honest with ourselves, and we said, all right, it's probably not the most correct way. So I ended up implementing this function here, which is just a function that reads my memory space, but you can see to start, it calls this lock access function, which is a mutex in the DLL, in this HMS driver, basically. And so that locks the data space. Then I can call my read, and then I call unlock, and then I return the data. So this ended up being the more correct way, but I did want to kind of show kind of the differences here. So these two arrays on the UI here are showing the API call versus the pointer call, and it's kind of moving fast, but they're displaying the same value. So, okay, that's pretty good. And the mutex didn't, or the lack of mutex didn't break anything, but still, you know, it's a risk we weren't willing to take because the trade-off was so minimal. So what I'm displaying here in these graphs is the time it takes to read, just a quick benchmark of how fast it took to either call this extas read or call my pointer. And this is in milliseconds. So what we're seeing is the API took about 5 microseconds, 5 to 6 microseconds on average. Whereas the pointer took about 1 microsecond. So 5 times faster, but on that scale, 5 microseconds. In this particular instance, we were just trying to pull the thing at 1K. So 5 microseconds versus 1 microsecond. We decided to go safe with the mutex, but still kind of showing the difference in that. And realistically, the speed issue here was probably just waiting for the mutex for the most part, I would imagine. So the thing I want to highlight here is this was when I had access to the source code. So I could go in and I could modify the DLL. But as Michael was saying, is sometimes people release DLLs and they don't give you the source. And so you're just stuck with their interface. And so you kind of got to, play the cards that you have. And in that case, you might just get a pointer to this memory space, and the memory manager might be the best way to go. Yeah, all right. So next one. So quick little StarGoat plug. So this is a very high level representation of the StarGoat architecture. And really what I want to highlight here and what we're going to look at is developing a CVT, a current value table for this application that acquires data and then does stuff with said data. So here's an even more simplified version. We have data producers like DACMX, OPC, Profinet, and then we have data consumers, and sometimes those consumers can also be producers. So those are the green boxes here. So like a calc might take a DACMX value and multiply it by an OPC value for some reason, and then it's going to create a new channel and write that back to the CVT. And so you get this current value table of what is the instantaneous value of all of these different channels. And then we have maybe the blue box is just an example of something that's only a consumer. So the sequencer is just reading data and making decisions based on the current state of the system. So the design here is, okay, how do we build this CVT? Spoiler, might have to do with the memory manager. But things we're considering, so you're going to have one writer per memory space. That's simple enough. DACMX is going to write its data, but you're going to have many readers. So you might have 2 calcs that are depending on the same channel, or you might have a calc and your PID are looking at the same channel. So you have to have parallel read access. So far, DVR might work. And as I mentioned, StarGoat is for aerospace testing. It's on RT, highly deterministic. It needs to be fast. We need to be asynchronous. Okay, so let's start with just considering DVR. So that's kind of the standard go-to when you need data by value or by reference in LabVIEW. So you create a DVR, now you've got a quote-unquote pointer to that memory space. So one DVR to rule them all. What if this whole CVT was a DVR? First issue with that, or the biggest issue, the only issue that matters, is your writers are going to block each other. So your DACMX goes to write to the DVR and the OPC tries to write at the same time. They're going to fight and they're going to end up slowing each other down. And if you have many, many writers, that's just a recipe for just a lot of, not deadlocks, but a lot of just waiting around for things to unlock. So the question was, could you write to a queue and then would the queue be fast enough to update the CVT? So let me try to envision that. So basically you have all of these producers and they're writing to the same queue, and then in parallel, you're flushing that queue, getting all of the values and indices out, and then updating the DVR in one swoop.
Right?
Correct, yes, that's the goal, is the table with current values. So in this case, there's no UI. We're doing, and I will say for the sequencer, our spec is to be able to respond to events at 1 kilohertz. So yeah, correct. This is instantaneous value. There's actually, we'll get into it, but yeah, there's a different queue for logging lossless, but this is just instantaneous value.
Right. So you need some frequency. The frequency with which you need to read the CVT looks to be smaller than your writers can do the writes. That's the case.
The frequency at which you read the CVT is smaller, like slower, than what you write to it. Potentially. I mean, the way to just get into kind of the weeds here, the way the loops generally work is you've got a writer or a DACMX AI loop that runs at 1K. It could be acquiring at whatever rate, but it's running at 1K.
Consumers need to hold the data, or apparently not, right?
They need some of the data.
Some of the data with much lower frequency than the data is produced by the producer.
Not necessarily. So this loop, this DACMX loop is running at 1K. Let's say it's getting a 10 kilohertz AI data, but it's running at 1K, so it's getting 10 samples per loop.
They have different frequencies. Your producers have different data generation frequencies, correct?
Yes, yes, yes.
But in your table, you want to read with some single frequency.
No, I mean these are all asynchronous loops here as well. The calc and the algorithm, the algorithms might be like a PID running asynchronously.
You want to really be able to read the CBT with the fastest consumer frequency.
Yes, yes, that is.
Frequency is slower than
No.
many of those producers. Otherwise, why would you want them?
Well, yeah, that's some of them, yes.
When you say current value, current is at certain moments in time.
Right.
So
Wait, so where are we going with this?
Still discrete.
Yes.
So, but you're okay with the loss.
Yes. Yeah, you're not getting all of your data.
For that CVT to serve all your consumers, right? It needs to be updated. It needs to be taken all the data, but to be able to send it, okay, to give an opportunity for the consumers to get the data for the highest frequencies, the highest frequency the consumer wants. The data.
Yeah, the producers have to run at least as fast, if not faster, than the fastest consumer. Correct. Yes.
So can that be handled with a queue?
Maybe.
Or maybe with lossy queue?
Question?
How do you know that the data from each of your instruments is the same type?
They are not the same type.
Because if you're using a queue to transmit that data to the consumer and puts it into your CDD, that queue has a type.
Well, you can make it universal, then interpret it. You can put that
So
on.
now you're adding processing data before and after.
Yeah.
Yeah.
Of course, everything has a cost. So I'm wondering how this is faster or.
Well, it's just one less step, essentially. When we start looking at the memory manager, right? With a queue, now you have to have a process to serve as a queue. So now you've introduced a middleman for what benefit? Now, I will say, as I said in the past, I haven't benchmarked, that A versus B there. So that could very well be a solution. This is what we landed on, but it's definitely not like the only solution. For by any means.
If I can remember that memory functions is the solution to produce a CVT which can accept writings very fast.
Yes. Yeah. Yeah, one of this. Yeah, exactly. And I did do some benchmarking on that. Yeah, go ahead. Yeah. Yeah, it runs on Cerio, RT-Pixie, and Windows as well. In the back, in the yellow, yeah, hello? Is that how Veristan works? Yeah, because Veristan's got like that root loop or whatever that runs at 1K, and it just gives you all of the data at the beginning of that loop. I don't know if that's an endorsement or not. I don't know. No, I've heard good things about Veristan. Yeah, no, yeah, you can get into a situation where you have stale data potentially. Yeah. Cool. Well, I appreciate the engagement.
You overwrite data before you want.
Yeah, you might miss cycles. Yeah, that is one downside of the hyper asynchronous architecture is you're not synchronous. Okay, I'm gonna go ahead and continue. Okay, so again, if we're just talking about DVRs, and I do like the queue thing, and maybe we can whip up something to look at that. So the other thing we explored was, okay, well, one, we ruled out one DVR to rule them out. I didn't want to block things. So the other thing I considered was one DVR for each memory space. So basically each of these blocks here would be a separate DVR. And then if I wanted to read from a particular channel, I would go in and I would have a lookup table that tells me this channel is at this DVR inside of this index. And it worked, but it's kind of a pain, and we'll see that. So I wanted to prove that this was actually the correct decision, and I've been wrong before. I don't know if I'm wrong now, but I've been wrong before. So I did some benchmarking, and I set up a benchmark that initialized an array of size 100,000, 10,000, up to 100,000, and then did a DVR write in a loop, and then I spawned 10 slaves that did the DVR read asynchronously. So we have one writer, 10 readers, and I did the same thing for the memory manager, and I benchmarked read and write speeds. So surprisingly, they were actually pretty comparable. And actually, this is on Windows, and I ran it on RT, and they were even more comparable. But what you do see, ever so slightly, memory manager does come out on top, but I was hoping it'd be a lot more, to be honest. So, okay, they're comparable, but again, going back to if you're doing the DVR solution, you might need to access, so let's say you have a consumer that needs data from that's from producer 1, 3, and 4. So that's now 3 DVRs that you have to access, dereference, and get the data from. Whereas with the CVT, with the memory manager, if I want to read those 3 pieces of data, I just go and kind of surgically go grab a single element, and feed them to my consumer. So we'll see here in a couple examples. So I've actually got some pseudocode. We're just going to go straight to the LabVIEW. No one uses text-based. So what does it look like to do that strategy if you have multiple DVRs? So here I have a request for channels. And then I have a map, this map that I talked about, where it's a channel name that tells you the DVR where that channel is, and then inside of that DVR where it is. Then I do a little bit of sorting so that I'm only reading each DVR once. And I'm also storing this return order, which we'll see used down here. So then now I have a map of all of the DVRs that I need to access, and then the channels within that DVR that I want to access. So then I go dereference that DVR, and then I index out my data, and then I build this little intermediary cluster where I store the return order on top so that I can call this sort array so that I can actually get the data out in the order that I requested. And so you'll notice I turned on profile buffer allocations. I don't know if y'all are familiar with that, but these little black dots here show you where LabVIEW is making a memory copy. And so the big ones are, when you dereference the array. I don't know why there's one here. Let's call that one fake news. But then you get one here. And one here as well. So essentially you get a bunch of these memory copies, and if you have a bunch of data that you're trying to get out, especially here, because this is getting that whole chunk of data. Excuse me. I don't like it. It's ugly. It's messy. So what does it look like for the memory manager? Well, it's nice and clean. It's pretty. It's simple. I'm a big fan of keeping things simple and readable. I think readable code is much better than clever code, in my opinion. We can talk about that more offline. So all I'm doing here is I get my channels, and then I loop over them. And then for each channel, I have a lookup that tells me the address. And then I go read that address, and boom, I have one buffer allocation for the whole operation. And then the other option is I can actually just read the whole array, and then I can do the same thing. I get my address by map, and then I index them out. And the thing that I mentioned this earlier, I was surprised to see, but it makes sense. There's no buffer allocation here. The buffer allocation happens when you pre-initialize the array. So LabVIEW is actually smart enough to know to actually use the same memory space, which I think is pretty cool. And again, so at the end of the day, you of course you have this pre-allocated one, but you do that before, so it's not dynamic, so you're totally fine there. And then you output your data. Okay, so then there's this one. So this is with the memory manager, and it's an optimization that you can do, optimization in very heavy quotes, where you can look at your channels and then get the indices out and then do a bunch of sorting to find contiguous chunks of indices. And then you can, down here, just read each chunk individually. But then you have to end up doing this kind of sorting stuff. And long story short, don't do this. I think this is not simple. This is too clever. All right, so that pretty much wraps things up. I have one more slide, and we're kind of going over, so I'm not going to spend too much time here. But I did end up expanding the memory manager to support 2D arrays, and we ended up using this as a 2D FIFO and what we call a 2D history buffer. FIFO is essentially just a queue. The history buffer uses kind of the same structure, but it doesn't dequeue things. It's just a circular buffer that remembers the last X amount of data, depending on how big you declared your buffer size. So these have been really helpful tools. And that we've used in Stargate as well. But in the interest of time, that's all I'm going to say about it. Thank you, guys. Yeah, any questions before I call it there? Oh, yeah. I'm using the LabVIEW memory manager, yes.
Are you planning on adding, suggesting changes to this?
To the repo? To be honest, no, but I'm not opposed to it. It just hasn't been something. So if I'm like being honest, this isn't something I use every day. This is a cool tool that I was excited to share that I, wrote in Stargate a couple years ago, and yeah, but it's not something I actively mess around. I do try to find opportunities to use it because I think it's really cool and it's handy, but I think it's more niche than it's something in your toolbox, not something you're gonna use every day necessarily. Yeah, no, it is. Yeah. Mm-hmm.
How do you get the one, the CPT that is open source? Some feedback mode there that do all this once, do all the parsing once, store it in the shift register, and then just calling in the code.
Yeah, like this, all of this sort, the pre-sorting, basically. Yeah. So we actually do a flavor of this in a different form. But yeah, what we do is we create what we call an address, which it's more complicated than that. But basically, yeah, it does the pre-sorting and it stores the lookup and the contiguous chunks in a class. And then when we call the read, we already have that kind of pre-done. And that's all in the spirit of kind of like, we don't care how much work it takes before steady state, but once you're in steady state, we don't want to be doing repetitive calculations. And yeah, absolutely. All right. Thanks for your time, guys. That was fun.